Hello, Professor, and welcome to our presentation. I am Özkan damdelen, and my partner is Muhammed İkbal Ceyhan. According to the assignment guidelines, the sum of our student IDs modulo 3 equals exactly 0. Therefore, we are assigned to implement and analyze the TCP-Tahoe algorithm. Before jumping into the test, let me briefly explain our system architecture. We built a robust state machine in C. For the network topology, we used the provided configuration files. If you look at our screen, specifically the a.conf file, node A listen on port 1001. It also maps out the routing costs to neighbors like B, C, D, and F. In our node.c file, the load_config function reads these parameters dynamically. This setup allows us to skip unnecessary UI elements and focus entirely on the mathematical evolution of the congestion window, which is the core of TCP/Tahoe.
To summarize our findings and provide a closing argument, through this assignment we practically observed that TCP-Tahoe is highly conservative algorithm. It prioritizes network stability over throughput. Resetting the window to 1 after every single package lost causes the massive underutilization of bandwidth. The implementation clearly showed us why Tahoe is most obsolete today, and why modern algorithms like Reno and Neuron were developed to include the fast recovery mechanism. This concludes our presentations. Thank you for time for watching our demonstration.
Now it's my turn again to demonstrate the tree-duplicate ACK scenario. This is perhaps the most critical defining feature of TCP/Tahoe, especially when compared to newer algorithms like TCP/Reno. Tahoe does not include a fast recovery mechanism when it receives tree-duplicate ACKs. It assumes that a packet is definitely lost and treats the network congestion as severe. If you look at our onDuplicate ACK function on the screen, the logic is very strict. Instead of cutting the window in half and recovering quickly, it brutally resets the CWND back to 1.1. Let me show you this live. I'm running our duplicate ACK test on the terminal. As you can see in the trace, everything is fine until run 6. At run 6, the third duplicate ACK hits. The algorithm immediately calculates the new SS thresh as 2.00 and drops the congestion window all the way down to 1.00. It then enters the slow start phase again. By round 8, the window successfully reaches the threshold, and the state safely transitions into congestion avoidance. This proves our state machine works perfectly.
Thank you, Özkan. Now I will explain how our code handles the timeout scenario, which is one of the most critical events in congestion control. In network communication, a timeout indicates a severe problem. It means a package was completely lost and no feedbacks were received from the receiver. TCP Tahoe interprets this absolute silence as heavy network congestion and handles it very aggressively. If you look at our on timeout function in the C code, which is here, you can see the exact mathematical response. First, the SS thresh, our slow start threshold, is heavily penalized and immediately reduced to half of our current congestion window size. More importantly, the CVND itself is forced to drop 1.0 maximum segment size here. More important, and the system transition completely back to slow start state. Tahoe essentially hits the panic button and starts over. Let's observe this in action on our terminal. I am running the timeout test event. Our simulation begins in the slow start phase. Look at the round 5. This kısım. Our Windows has successfully grown to 6.0, but suddenly at round 6, a timeout occurs exactly as the algorithm dictates. Tahoe takes the immediate action. It updates the SS thresh to 3.0, which is half of our previous window, and drops the window size exactly 1.0. As you can see in round 7 and 8, the algorithm enters the slow start state again, increasing the window size one by one to cautiously probe the network capacity. This demonstrates the Tahoe strict start from scratch policy during the severe package loss.